Someone once said, as our computer simulations become more and more advanced and lifelike, at some point our simulations will become indistinguishable from reality. My response to his statement was, if this is the case, how do you know it hasn't already happened? If you understood how our universe functions on a quantum level, and understood how computer simulations function on a quantum level, you would have no doubt in your mind that the thought of humanity living in a computer simulation, right now, is very plausible. But reality possesses just enough detail to convince its observers otherwise. But don't worry. In our breakdown of the details that persuades people into believing reality is an objective thing, we will look deep into every persuading factor for what reality is, that being, simulated information expressed through numbers, mathematical descriptions, in the form of quantum binary code. Yes, the same thing that drives the realism of our computer simulations, that is, subatomic particles and binary expressions, is the exact same thing that drives what we call the universe. Although it may seem unbelievable, it is nevertheless the truth. In order to show the viewer the true nature of physical existence, and how it aligns with the nature of our computer simulation technology, a breaking down of both physical existence and computer simulation technology to their last components are in order. And this will be done with the unfolding of this documentary. According to the study of particle physics, we live in a physical universe of particles, matter, and forces. But, when particle physicists start off their discoveries about our universe, they do not start off with established self-evident truths about particles, matter, and forces. Rather, they begin their discoveries in a much deeper underlying realm of reality. The realm I am referencing is a dimension of our universe that is pure mathematics. And understanding what is more fundamental, that is, understanding what is underlying what, is crucial in comprehending our universe as a computer simulation. Let the viewer understand, nature is not just mathematical, but extraordinarily mathematical. And in an objective reality, one might beg to ask the question, why? Why is nature so extremely mathematical? But on the other hand, in a computer simulation, an extremely mathematical reality makes perfect sense. In a computer simulation, not only would the fundamental level of the simulation be mathematics, but the entire structure of the simulated system would function through mathematics, as our simulated reality does. Scientists have for a very long time been using mathematics to describe the physical properties of our universe. An example is drawn from the Industrial Revolution and an Austrian physicist named Ludwig Boltzmann. Before the discovery of the atom in 1905 by Albert Einstein, the Western world had entered the Industrial Revolution, which was powered by steam. By the 1850s, steam was changing the world. It was powering the mighty engines, the trains, the ships, and the factories of the industrial age. Therefore, figuring out how to use steam more effectively became a matter of not only commercial significance, but military significance as well. How steam worked from a fundamental level became a key question in 19th century science. The demand to build more powerful and efficient steam engines created an urgent need to understand and predict the behavior of water and steam at high temperatures and pressures. Ludwig Boltzmann, a physicist mostly remembered for his role in the development of statistical mechanics, and the statistical explanation of the second law of thermodynamics, said to his colleagues, "If you imagine steam as millions of tiny rigid spheres, then you could create some powerful mathematical equations. And those equations would be capable of predicting the behavior of steam with incredible accuracy." Boltzmann was right. The imaginary rigid spheres he told his colleagues to calculate with, we today call them atoms, the building blocks of steam and all physical existence. Another example of the importance of mathematics in describing our physical universe is taken from classical mechanics. To show how planetary bodies and forces function in our universe, in the 17th century another great physicist named Sir Isaac Newton developed a special math called calculus, a math necessary to perform the mathematical calculations involved in classical mechanics. calculus mathematics is used today in our computer simulations. Another example can be drawn from the late great polymath and philosopher Gottfried Leibniz, who first figured out the mathematical form of what we today call kinetic energy. Kinetic energy is the energy all physical bodies possess due to their motion. The kinetic energy of a body is equal to the work required to bring the body from rest to its motion. Gottfried Leibniz described kinetic energy as the vis viva. In Latin, this is to say, the living force responsible for the motion of bodies. Its mathematical expression is shown as mv2. His expression expresses the product of the mass m of the object by the square 2 of its velocity v. Mathematics has been used to predict, and therefore, discover many things about our universe. Example, the existence of the planet Neptune, radio waves, the Higgs boson particle, and the list goes on and on. One last example is drawn from the study of quantum field theory, QFT. It is shown in QFT that the universe is made up of energy fields, an electromagnetic field, an electron field, a Higgs field, etc., etc. Physicists have never seen these energy fields, yet they say these fluctuating fields of energy are all around us because the math shows they are. And accurate predictions made by mathematical equations drawn up in QFT prove these energy fields are all around us. Note, QFT has made some of the most accurate predictions in all of science. I state all of this to share with the viewer, the sciences that deal with the nature of our physical reality rely heavily on mathematics. Physicists, the scientists whose vigorous studies concerns the nature of reality and the properties of matter and energy, rely so much on mathematics for their investigations, predictions, and discoveries, one might come to believe the entire universe is mathematics.
If I were a character in a computer game that was so advanced that I were actually conscious and I started exploring my video game world, it would actually feel to me like it was made of real solid objects, made of physical stuff. Yet if I started studying, as the curious physicist that I am, the properties of this stuff, the equations by which things move, and the equations that give the stuff its properties, I would discover eventually that all these properties were mathematical. The mathematical properties that the programmer had actually put into the software that describes everything.
Like how an object floats, bounces, or crashes, are only mathematical rules created by a programmer. Ultimately, the entire universe of a computer game is just numbers and equations.
That's exactly what I perceive. In this reality, too, as a physicist, that the closer I look at things that seem non-mathematical, like my arm here in my hand, the more mathematical it turns out to be. Could it be that our world also then is really just as mathematical as the computer game reality? Many of my physics colleagues will say that mathematics describes our physical reality, at least in some approximate sense. I go further and argue that it actually is our physical reality, because I'm arguing that our physical world doesn't just have some mathematical properties, but it has only mathematical properties.
Here is a photo taken of a simulation. A pendulum smashing through a brick wall. The behavior of pendulums is pretty simple, straightforward, and easy to predict. But predicting the motion of all these bricks, however, is much more complicated. For example, we may need to know the precise moment when each brick will fall. One of the main goals in physics is to make predictions. But calculating an equation with paper and pencil for the motion of each of the bricks here can become very difficult and convoluted. High school and college classes on physics teach students how to deal with relatively simple situations. In simple cases, it is possible to calculate elegant equations for the motions of objects. But with extremely complex situations, computer simulations are performed to draw out extensive outcomes. Note: computer simulations are used for adequacy and time efficiency. But any simulation can in principle be done by hand with pencil and paper. Although executing a simulation of the entire observable universe by using paper and pencils would be extremely time-consuming, it could theoretically be done in principle. So, what exactly is a computer simulation? Is it not the reproduction of the behavior of a system, by using a computer to simulate the outcomes of a mathematical model associated with a said system? A computer simulation is the use of a computer to represent the dynamic responses of one system, by the behavior of another system modeled after it. A simulation uses a mathematical description, or model, of a real system in the form of a computer program. This model is composed of equations that duplicate the functional relationships within the real system. When the program is run, the resulting mathematical dynamics form an analog of the behavior of the real system, with the results pre-sent it in the form of data. A simulation can also take the form of a computer graphics image that represents dynamic processes in an animated sequence. Computer simulation, Britannica. Today, computer simulation usage is commonplace in the scientific community. Technology has replaced our obsolete, traditional paper and pencil mathematical modeling with computer event simulations on scales that would have been thought to be unimaginable some 50 years ago. The scale of events being simulated today exceeds anything imaginable in the past using paper and pencil mathematical modeling. For instance, through the Department of Defense's usage of multiple supercomputers, over a decade ago a desert battle of one force invading another involving the simulation modeling of over 66,000 tanks, trucks and other vehicles on a terrain around Kuwait was simulated. In 2005, a more highly scaled computer-simulated model was created, the 2.64 million atom simulation model of the complex protein-producing organelle, ribosome. If we keep advancing with the knowledge of knowing that everything in the physical universe can be simulated, it seems inevitable that eventually we will simulate ourselves. And this has already begun in Switzerland. A little over a decade ago, the Blue Brain project at EPEL in Switzerland was introduced. This project is the creation of the first detailed computer simulation of the human brain, right down to the molecular level.
The human cortex is organized into specialized regions. We need to understand what these different regions are doing. Some are specializing for language, some are specializing for vision. So we will create systematic maps of the human brain, trying to understand each of these subsystems and trying to understand what are the specific parameters so that they can ultimately be brought to simulation.
Another project termed the Illustrious Project, an ongoing series of astrophysical simulations run by an international collaboration of astrophysicists, with the goal of piercing behind the curtain of the evolution of the universe, spanning from the initial conditions of what is termed the Big Bang all the way to present day, some 13.8 billion years later. Completed in 2013, the Illustrious Project is the most advanced computer model of the universe ever created. The simulation uses a state-of-the-art numerical code and a comprehensive physical model. On a supercomputer it took 3 months to run the program. That's equivalent to more than 2,000 years on a home computer. The project's aim is to better understand the nature of our universe, including galaxy formation. In a nutshell, a simulation is the mathematical model of a real system. I cannot stress enough to the viewer that numbers, mathematics, is the language to any computer simulation. A simulation uses a mathematical description, or model, of a real system in the form of a computer program. The model is composed of equations that duplicate the functional relationships within the real system. Now, concerning numbers, mathematics, and our universe being a simulation, take our Sun and Moon as an example. At enormously different sizes and distances from the Earth, the Sun and Moon appear the same size in Earth's sky, making way for picture-perfect total solar eclipses. Is this by chance, or is it by design? The total solar eclipse phenomenon has taught us much about our universe. Without perfect eclipses, we might still be in the dark concerning much about our universe. Helium, the second most abundant element in the universe, was discovered, not on Earth, but rather, on the Sun by Pierre-Jules César Janssen, a French astronomer who noticed a yellow line in the Sun's spectrum while studying a total solar eclipse in 1868. Therefore, studying an eclipse is how we discovered the atom element helium. History will probably never allow us to forget Albert Einstein's discovery, with the help of Frank Watson Dyson. The two used the total solar eclipse of 1919 to prove a warping of spacetime by the Sun's mass, showing the world, gravity is due to a warping of spacetime, and not a direct attraction as had been taught for prior centuries through Newtonian mechanics. Someone once said, the universe was designed to be discovered. And once you have studied eclipses and has borne witness to the Sun's corona in its entire splendor, anyone with an understanding of electromagnetism would say, the Sun's corona is a huge electrical phenomenon, a blessing through discovery, and worthy of study. The dimensions in reference to the Sun and Moon's alignment during a total solar eclipse must be an exact number in order to see the perfect corona of the Sun. In other words, any old dimension just won't do. Yes, all numbers must bear a precise relationship in the alignment of the two solar bodies in question to exhibit a total solar eclipse. If it is not precise, the Moon might appear too big in the sky, blotting out the entire Sun along with some of its corona. On the other hand, if the Moon appears too small, the corona wouldn't be able to show in all its spectroscopy, which is a spectrum produced when matter emits electromagnetic radiation. Therefore, the way our simulated reality is designed, the diameters and distances of the Sun and Moon are equivalent. Although the Sun's diameter is 400 times greater than the Moon's diameter, the Sun's distance is 400 times farther away from the Earth than the Moon, causing them both to appear the same size in the Earth's sky and allowing for perfect total solar eclipses. Concerning the dimensions of the diameters and distances of the Sun and Moon, National Geographic has associated this phenomenon with cosmic chance. But I beg to differ because these types of mathematical occurrences are vast throughout the cosmos. May the viewer understand, we find this sort of number arrangement throughout our physical solar system. It is not taught, or even mentioned by mainstream science, mostly because it cannot be soundly explained, unless we observe our reality as a mathematically constructed simulation. Only through the hypothesis of a computer-generated universe will we come to understand why, with the shifting of a decimal point here and there, our solar system comes to life with special corresponding numbers around every corner. Another example can be drawn from the diameter of the Sun and the time found in a day. The Sun's diameter is 864,000 miles across, 864,337.3 miles to be precise. Now let's take the length of time found in a day. If our reality is not a computer-generated simulation, the diameter of our Sun should have no relation to the length of time found in a day. Yet there is 86,400 seconds in a day. The only difference between the diameter of our Sun and the length of time in a day is really the mere shifting of the decimal point to the left or right. And there are many other examples that can be brought to the table, which reveals our reality as a computer-generated simulation. For instance, take the phenomenon of the expansion of space, and note, it gives implications of a digitized universe. We know from the American astronomer Edwin Hubble's discovery in 1929 of the Doppler shift interpretation of the observed red shift of galaxies, Hubble's law, that space itself is expanding. Other than our neighboring galaxies, that is, approximately 30 galaxies locked in orbit with our Milky Way, all galaxies are moving away from the Milky Way at tremendous velocities and appear to be picking up speed in their travels. Cosmologists and physicists are telling the world, with the continual upgrade of velocity of the expansion of space, one day all the foreign galaxies we can view today will be too far away and moving too fast from us to be seen, even with our best scientific instruments. This is because, if the velocity continues to upgrade, one day these foreign galaxies will be traveling just as fast if not faster than the speed of light. And the light illuminating from foreign galaxies will not be able to travel fast enough towards the Milky Way to reach us. One of the most powerful truths about Hubble's discovery of a runaway universe is this: as the foreign galaxies travel away from our Milky Way, these foreign galaxies' velocities are proportional to their distance. What this means is, if a foreign galaxy is twice as far away from the Milky Way, its velocity is twice as fast. If a foreign galaxy is 3 times the distance, its velocity is traveling 3 times as fast. In astronomy terminology, a megaparsec is equivalent to 3.26 light-years. And according to Femilab, if a galaxy 1 megaparsec away from our Milky Way is moving at 70 kilometers a second, a galaxy 2 megaparsecs away is moving at 140 kilometers a second, and a galaxy 3 megaparsecs away is moving at 210 kilometers a second, and so on, and so on. An expanding space that gives off a proportion velocity throughout the cosmos gives reference to something not objective, but rather algorithmic and digital even. Another example of our reality showing similarities of a number-based simulation can be seen in the ratio of the size of the Earth to the size of the Moon, and their connection to what is termed in mathematics the Pythagorean theorem, a theorem attributed to Pythagoras, which states the square of the hypotenuse of a right triangle is equal to the sum of the squares of the other 2 sides. Let the reader understand, the Pythagorean theorem is a simple equation with enormous application. It is the core of much of geometry. It is also the foundation for trigonometry. This triangulation is used to this day to pinpoint relative location for GPS navigation. And yet, we find this same theorem corresponding to the ratio of the size of the Earth to the size of the Moon. Probably the most interesting thing about the Earth-Moon ratio corresponding to the Pythagorean theorem is the right triangle's hypotenuse summing up to one of the most powerful and interesting numbers in all of mathematics. The number I am referencing is phi, which is 1.618. Phi is also known as the golden ratio. It must be noted that phi is a number that has fascinated mathematicians, scientists, architects and even artists for centuries because of the many strange places the number appears in nature. Phi popping up in the Pythagorean theorem triangle's hypotenuse, in relation to the Earth and Moon's ratio, makes the simulation hypothesis even more plausible. Throughout the centuries there have been great minds that believed, and even taught, our physical reality is forged upon numbers, mathematics, equations, etc., etc. Was it not the Greek philosopher and mathematician Pythagoras, the creator of the Pythagorean theorem, who said, "All is number"? Pythagoras taught us some 2600 years ago, numbers are the ultimate reality, and everything is related to mathematics. These may seem like random numbers, but they are all a part of what is known as the Fibonacci sequence. These numbers are a series of numbers developed by a 13th century mathematician named Fibonacci. And the numbers coincide with the number phi and the golden ratio discussed earlier. We find this number sequence in nature so often, it seems evolution favors these numbers. Counting the scales in a pine cone gives you this Fibonacci sequence. And counting the scales in the opposite direction gives you an adjacent Fibonacci sequence. You can see the same on a sunflower head. 2 sets of sparrows going in the opposite direction. Both Fibonacci and adjacent Fibonacci. Another number that have found favor in nature is pi. On average, a river's winding length from its source to its mouth, compared to its direct distance, seems to be the number pi. Both light waves and sound waves incorporate the number pi. The number pi tells us which colors will incorporate a rainbow, and what the C key should sound like on a piano. Yes, even music theory has its parallel in mathematics because common mathematical patterns exists in music. By measuring the lengths of the vibrating strings, it was Pythagoras who said, beautiful musical relationships become in essence beautiful mathematical relationships. For instance, in an octave, the string's length create a ratio of 2 to 1. In a fifth, the ratio is 3 to 2. And in a fourth, it is 4 to 3. The current of thought Pythagoras generated through his revolutionary approach to how life and the universe operates led to all mathematical science in the Western world. Thousands of years ago, Pythagoras saw that the information held within numbers was the essence of all things and presided over the entire universe. Also, the Italian philosopher, physicist and mathematician of the 17th century, Galileo Galilei has said, "Mathematics is the language with which God has written the universe." The reason why our reality is so mathematical is because, at its most fundamental level, reality exists as entropic information, expressed through numbers and mathematics, as it is in our man-made simulations. In a computer simulation, number crunching is a necessary process. Be on the lookout for part 2 of this documentary series, as we probe even deeper into reality, with the notion of humanity living in a simulation. Be sure to like and subscribe, and thanks for watching.
Have you ever questioned the reality of the world around you? Are we living in a computer simulation? Digital reality. Our Universe is a Simulation by Michael Cage. In this thought-provoking book, author Michael Cage explores the concept of digital reality and the possibility that our entire existence is just a simulation. With a blend of philosophy, science, and technology, digital reality takes you on a journey through the history of virtual reality and computer simulations and explores the implications of living in a digital world. Join the discussion and challenge your perceptions of reality. Get your copy of Digital Reality today. Available now at all major bookstores and online retailers.